Hey everyone, this is the 6-1 to 6-6 practice problems for the quiz. So I hope that you're able to zoom in a little bit on this video. This app that I'm using to record this doesn't allow me to zoom my camera in, so I'm gonna apologize that it's kind of small, but hopefully you can figure that out. Okay, so number one, this is from section 6.1. So this is the first part of this chapter where you have to be able to write a sample space and be able to find a simple probability based on that sample space. So I'm going to explain that as we go. Two fair six-sided dice are ruled. The faces of each die are numbered 1 through 6. Consider each event. So event A, the sum is an odd number. So it says write sample space, write the sample space and find the probability of A. So the sample space is just the list of all possible outcomes that would have this as their event. So the sum is an odd number. So I'm gonna start thinking of when I roll 2 dice, okay, when would I get an odd number, or what would my odd numbers be? I could get a 3, 5, 7, 9, or 11. So I'm gonna think about how could I get a 3? So I can't get a 1 because I'm rolling 2 dice. So how could I get a 3? I could have a 1 and a 2, or I could roll a 2 and a 1. That's it. How could I get a 5? I could do a 1 and a 4. I could do a 4 and a 1. I could do a 2 and 3, or 3 and then 2. So this is my sample space, all possible outcomes. How could I get a 7? I could do a 1 and a 6, a 6 and a 1, a 2 and a 5 and a 2, 3 and a 4, 4 and 3, and I think that's it. That's how I can get a 7. All right, a 9, I could do a 3 and a 6, a 6 and a 3. I could do 4, 5, 5, 4. That's it. And then 11 would be 6 and 5, or 5 and 6. Those would be all my possible outcomes within this particular event. So the probability is, we know that if I roll 2 dice, there are 36 different possibilities, because there's 6 for the first one and 6 for the second one, so 36 total. Okay, and then there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 18 in this particular event, so the probability of that would be 1/2. Okay, and then the next one says that event B is when we roll, the first roll is an even number. So my even numbers are 2, 4, and 6. Okay, but I could roll 2, 1, 2, 2. The other number doesn't matter. So 2, 4, 2, 5, 2, 6. Okay, or 4, 1, 4, 2. 4, 3, 4, 4, 4, 5, 4, 6, and then 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So there's 6, 12, 18 different outcomes in this event out of the 36 total. So again, the probability for that one is also 1/2. So that's just basic, write the sample space. So what are the possible options? And find the probability of those sample spaces. So that's from section 6.1, sample space and probability. Then the next section was 6.2, and we are talking specifically about the words union and intersection. So a union is like a joining of, I think of it like a union of 2 people is like a joining of 2 families. So joining all the outcomes together. And then intersection is where the outcomes overlap each other. Okay, so that's what you need to know about joining or union and intersection. All right, so it says write the sample space for the union, okay, of A and B. Another way you might see it is A or B, okay, or you might see it A, U, B. All of those things mean the same thing, and it means union, so it means I'm joining all of those outcomes together. I don't want to repeat anything though. So basically, I'm taking all of the event B and all of the event A and writing them down. So I'm putting them all together and writing them down. But again, I'm not repeating things. Like this 2, 3, see how it's in both? I'm not gonna write that twice, I'm just gonna write it once. So if you do this, you're gonna write all these, and then you're gonna write all of these that you haven't already used. Okay, so I'm gonna start by just writing all of these. And then I want you to go ahead and continue with writing whatever's left in here that we haven't already used, and we're going to put them together to make our union. All right, so these are what you should have gotten. So there's all of those. So there's 18 of those. And then there were 9 more from here that we hadn't already written down. So you should have gotten a total of 27 out of those original 36, which reduces to 3/4. That's our union of all of both of these events happening. That's our sample space, that's the probability. Okay, and then the second one is intersection. We're finding the intersection. Intersection means where do those things overlap each other? So we're looking at these 2 events and we're finding all of the ones that are overlapping, so are in both of these. Okay, you might see it say intersection, you might say it say A and B, or you might see it written like this, A, it looks like an upside down N, it looks like an N and then a B. Okay, really the symbol is like this, but I couldn't get that on the document to do that, so I just made an N instead. All right, so it's basically going to be those 9 that were overlapping both of these. I think there's going to be 9 of them. So the 2, 1. So any of these that are also in these are the ones here that start with an even number. Okay, so 2, 1, 4, 1, 2, 3. Any of them that start with an even number. 5, 4, 3, 6, 3, 4, 5, 6, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of those 36, which is 1/4. Okay, so then it says, are the events independent or dependent? So you can think about it, but also the best way to do it is just to test it using this equation. So the probability of, so I'm going to say this, if the probability of where they intersect is equal to the probability of A by itself times the probability of B by itself, then the events are independent. So if the intersection probability is equal to each one separately multiplied together, then it's independent. If it's not equal, then it's dependent. All right, so the intersection probability was 1/4. Probability of A was 1/2 and B was 1/2. So 1/2 times 1/2, which is 1/4. And since those are equal, this is independent. So that's the answer, independent. And where it says show how you know, you will have to do this. You're just going to do this equation right here and show that that is equal to that. All right, so that was section 6.2. And we went on to 6.3, where it's basically just find the number of possibilities Or find the probability that if you guess, if you guess on a test like this one, this is a test has 5 true false questions, 8 multiple choice questions with 3 choices each. What's the probability of answering all the questions correctly if you randomly guess on each question? Okay, so you have to figure out how many different possibilities are there, and then what's the probability of guessing the correct string, is what we call it, correctly. All right, so there's a way that I always think about this. Okay, I think about it like this. If you have 5 true false questions, number 1, number 2, number 3, number 4, number 5, they're all true false. So that means they each have 2 choices. So every one of those have 2 choices. And we're going to multiply these together to know that there are this many, 2 to the 5th power. That's how many ways that we can kind of put those in order, okay? It could be true, 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 true. It could be true, 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 false. It could be false, true, 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 true. It could be false, 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 false. I mean, there's 2 to the 5th power. That's how many different ways we could guess on this test if we were going to guess, either true or false. And then there's 8 multiple choice questions, and each one of them has 3 choices. So you could kind of lay it out the same way. You could say the first multiple choice question has 3 choices. The second one has 3 choices. The third one has 3. Oh, this is going to continue 8 times. So we're going to multiply all of these together. So that's going to be 3 to the 8th power. And we're going to multiply all of those things together to figure out how many different possibilities of answers that we could get here. So 2 to the 5th power times 3 to the 8th power is 209,952. Okay, so if it said how many different strings are there, or how many different possibilities are there to guess on this test, there's 209,000. But this one actually asks us, what's the probability of answering them all correctly if you guess every time the first time? Okay, it's 1 out of this. That's our probability. Number 5, a student ID number in Westerville City Schools is 10 digits long. I'm sorry, he's 6 digits long from 0 to 9. Each digit's 0 to 9. How many people can be assigned a number before they will have to start repeating numbers? So it's 6 digits, 1, 2, 3, 4, 5, 6. Okay, and each one you have choices 0 through 9, so you actually have 10 choices for each one. And we multiply these together to figure out our total number of different possibilities of numbers there are. So 10 to the power of 6 is another way you could write it, okay, which is 6 zeros. So 1 million. So basically they can have 1 million students before they have to start repeating those ID numbers, or they just add another digit, and that's going to give us a lot more choices. All right, number 6, 6-4. This is the number of possibilities without replacement, meaning that these numbers 10, 10, 10, 10, 10, 10 would not be the same. It would be like 10, 9, 8, 7, 6, because we're taking out a number and then we're not putting it back in. It's kind of like those marble problems that you saw on that activity that we did when we walked around the room. So a softball team has 11 players. How many different ways could the coach create a batting order? So a batting order is a list of the players from 1 to 11 who's going to bat. So the first person up, there's 11 choices for that person. But then the second person up, there's only 10 choices for, because we've already used one of them. And then it continues all the way down until the last one is just whoever's left. And you're going to multiply these numbers together. Another way to think of that is called 11 factorial, which means the same thing, 11 times 10 times 9 times 8 times 7, all the way down to times 1. So if we multiply those numbers together, or if you do the factorial, you get 3, 9, 916, 800. 39,916,800 different ways you can line up 11 people. And then of those 11 players, how many ways can the top 3 in the order be chosen? So we're going to pick 3 from the top. This is a permutation of 11 players, and we're picking 3. Okay, so if you put that, there's a button on your calculator. Okay, on your calculator, the button is menu, probability, so number 5, and then permutations, number 2. And if we have 11 and we're picking 3, we do 11, comma 3. And you get 990 different ways. Now, if you have the TI 84s, you push math. I'll write it down. Sorry, I think it's math. Yeah, math. Then you go over to where it says PRB, probability, and then you go to the same thing, permutations. Okay, and then you can do the same thing. You should get the same answer. All right, 6.5 was completing and analyzing a contingency table. So this is when you have a table, or maybe you have to make a table. Oh, I just realized something, but that's okay. A technology group wants to determine if bringing a laptop on a trip that involves flying is related to people being on a business trip. Data for 1,000 random passengers at an airport was collected and summarized in this table. If you see a table, you also need to have the totals written down. So we need to add those together to get 329. That's the total for the laptops. And this is 671. That's the total for no laptops. And then 510, that's the total for traveling for business. And 490, that's the total for not traveling for business, and you should get a total of 1,000. What's the probability of traveling with a laptop if someone is traveling for business? So this part right here, we know they're traveling for business. That's what's given to us. So we are looking at the people who travel for business. That's 510. So our total number is 510. Those are the people we're looking at. And what's the probability that they have a laptop? That would be 236 out of that 510, which is like 71.7%. What's the probability that a person not traveling for business carries a laptop? Okay, same thing, not traveling for business, we're looking at 490. And that they're carrying a laptop, we're looking at 93. So if we add those, so this would be around 19%. Okay, and then number 8, I realized I was supposed to write 6.6. This is conditional probability. That's the section that it came from, if you want to look back at that section. Okay, and this is going to be really small probably. If Letitia studies for her math test tonight, she has an 80% chance of getting an A. If she does not study, she only has a 10% chance. Whether she can study or not depends on whether she has to work at her parents' store. Earlier in the day, her father said there's a 50% chance that Letitia would be able to study. Draw a tree diagram for the situation. Okay, so she's either going to study or she's not going to study. Okay, and there's a 50% chance that she would be able to study, so I'm going to put that probability on this line. So there's a 50% chance that she's not going to be able to study. And then if she studies, she's either going to get an A or she's not going to get an A. Okay, if she doesn't study, same thing. She's either going to get an A or not. But it says if she studies, she has an 80% chance of getting an A. So she studies, she's going to have an 80% chance of getting an A, which means she has a 20% chance that she's not going to get an A. Whether she can study, okay, earlier, no, sorry. If she does not study, she only has a 10% chance. So if she doesn't study, she only has a 10% chance of getting an A and a 90% chance that she's not going to get an A. So this is our tree diagram. This is all we have to do for the tree diagram. And then number 8B says create a contingency table with that information. So now we're going to make a table. Not gonna be very pretty, but that's okay. So she's either studying or she doesn't study. And she either gets an A or she doesn't. And then we have our total in this column, the total at the bottom. So to get the studying gets an A, we're going to multiply the study 0.5 times the gets an A 0.8. So 0.5 times 0.8, if we multiply those, we get 0.4. Okay, so you should probably pause this, make sure that you can get all these numbers, and then come back and check it. So go ahead and pause it. Okay, so I started filling this in, and then I realized I should probably make sure I explain this. So study and doesn't get an A. So study, 0.5, not get an A, 0.2. So I'm multiplying 0.5 times 0.2 to get 0.1. Okay, doesn't study, gets an A. So not study, 0.5, gets an A, 0.1. 0.5 times 0.1 is 0.05. Doesn't study and doesn't get an A, so 0.5 times 0.9 is 0.45. To figure out my totals, I add across. So this is 0.5 and this is 0.5, and then to get these totals, I add going down. So this is 0.55, and this is 0.45. My total should be in this bottom right corner, should always be 1. So if something is not right, then you can tell because of that number there. Then we're going to use this table to answer the questions. Find the probability that Letitia gets an A on the math test given that she studies. So we're looking at the column of when she studies. We know she studies, so it's 0.5 is going to be on the bottom. And she gets an A on the test, that's going to be 0.4, so that's going to be 80%. And then D, what are the chances that Letitia studied given that she got an A? So now we're looking at the fact that she gets an A, 0.45. And we want to know that if she studies, so we're going to go to that column, which is 0.4. So 0.4 out of 0.45 is 88.9. So if we know she got an A, she has an 88.9% chance of knowing that she actually studied. Find the likelihood that she does not get an A if she studies. So we know she studies, so we're going to this row. We know she studies, 0.5. Not get an A is 0.1. And if we divide those, we get 20%. There you go. Hope that helps.